Good evening, everyone, and welcome to AFI Victoria's June webinar. We are so pleased you've joined us this evening for what we are certain will be a fascinating and thought-provoking and ideally inspiring presentation. Before we launch into the presentation, there's a couple of housekeeping items. On the right-hand side of the screen, you'll see a little chat feature. This is a speech bubble, and this is able to be used for informal conversation or if in fact you have any technical issues. Beneath that, there is a Q&A feature, which is a question mark. Please use this throughout the presentation or at the end of the presentation to submit any questions you have of our presenters, and at the finale of the presentation we will come back and we will address each of these questions. So tonight we're joined by Matt and Shane Corish from Webcast Proprietary Limited, who've agreed to share with us their journey from early days of producing Mazda rotary IDA manifolds through to now, where they not only manufacture a broad range of rotary components, but also offer engineering and manufacturing services to clients, helping them to turn ideas, rough or refined, designs into components and then be manufactured into custom parts or to scale, including the V12LF. The team at Webcast have very successfully combined traditional foundry, moulding and manufacturing methods with the latest 3D printing technology available to produce award-winning and much sought-after automotive components. Before I hand over to our presenters, a little bit about them. Matt and Shane grew up in country Victoria, where they initially developed their passion for anything mechanical. Living out of town meant that they very quickly learned to repair and maintain equipment on their property, more often than not, finding creative ways to do so. Matt studied business systems at Monash and moved to the US, working as an IT manager for a large food manufacturer, while Shane studied manufacturing and engineering at RMIT, then began his working life as a contract engineer and more recently as the lead chassis designer for a large bus manufacturer. On Matt's return from the US, the boys teamed up again and pursued their automotive passions, thus forming Webcast. I'll now hand over to Matt.
Thank you, Amber, and thank you everyone for joining us today. It's a great honour, and I really appreciate people listening in. So the introduction really sums up how we got to this point of Webcast. What I wanted to show you is some of the things that we've done that really launched our business over the last few years. So I'll share a presentation. And if you let me know, Amber, when you can see that.
See that?
Yeah, we can see it.
Okay, great, thank you. So Webcast Engineering is all about pushing the boundaries of automotive engineering. We started out several years ago by visiting the SEMA show in America, really focused on our IDA intake manifolds for the rotary market. And what we noticed is this industry was far bigger than we could have imagined. But we also noticed some constraints. By this point, the custom car industry had reached completely new heights, to the point where people were building vehicles where every single component was custom. There were 3D printing trim components, not one panel would ever be left uncustomized, amazing paint, everything was done. But they were left stuck with one seemingly unbreakable constraint, which was that OEM castings. And being in the casting business ourselves, we thought this was really strange, seeing $1 million plus builds going forwards, but using over the parts counter engines from GM and Ford and Mopar. So we thought, let's see what we can do about this. Let's see what we can show off, how we can show off the Australian manufacturing capabilities and cast an engine that had never been done by an OEM. Now, the automotive aftermarket doesn't move that fast. It seems like it probably does. People are very set in their ways. So we thought, well, what can we do? So we took the #1 engine that was seen in these hot rods. Probably about 40 to 60% of the hot rods at this show, there's 2,500 vehicles at this show every year, had a GMLS engine. So we took that, measured it, and then using all of our skills and all of our partner organisations that we work with in Australia, constructed a 12-cylinder version. And I don't know about you, but to me, a V12 is the ultimate engine. So we look to do this using traditional pattern making, but as you'll see a little bit more at the CSIRO, when Shane talks you through some of our procedures, we were really stuck creating some of those complex molds. So the CSIRO helped us there with 3D printing sand, and you can see in this drawing here, or on the screen here, we have casting going through the CNC machine, the 3D printed sand up on the left. Shane's standing proudly with one of our engine blocks just after coming through a CNC machine, a finished product up there on the right, and one of our show vehicles being judged at the event. Now, how did this work? How did this change the industry? It really, really did. It put Australian manufacturing in that performance aftermarket right at a whole new level, which was our goal. And it changed people's thinking out and got people thinking outside of the box as far as engineering and these custom vehicles was going. Now, we saw that vehicle there, that's a V12 Camaro that we partnered up with a custom hot rod shop in the United States to build for the show specially. And it wasn't even in a very good position at the show. It wasn't a prime position because no one knew who we were at the time, but it became the most socially shared vehicle of the show. That's against, some of the biggest builders, people you see on TV every day. It got the attention of all of the media, the magazines, as you can see there were features from Canada, the United States, back home in Australia. It's really good to have the support of Street Machine magazine. And then we saw, some of our heroes from shows like Top Gear and Roadkill were blogging about this. So we were really, really happy to see, the change that we could push forward. So that launched our business into what we are today, which is where we make our own components, but we also consult with people who are looking to do similar things themselves and make their own mark on the industry with their own products. So we still make our original intake manifolds. That's the bread and butter of our business. We'll probably always be doing that. We make and market those V12 LS engines, which is our hero product that we talk about, and some other more complicated Mazda rotary components. But really, where probably more than half of our business is now focused is the services and consulting. We work with other companies to help them bring their designs up to scale manufacturing, or a product that can be manufactured at scale. We work with the CSIRO machinery there, doing rapid prototyping using that 3D printed sand. You'll hear a lot more about that in a few minutes. And we don't really do the traditional pattern making, but we make traditional style patterns using CNC machines. We sometimes use a hybrid approach between 3D printed and CNC pattern making. And lastly, we still perform automotive engineering. That's really our passion. We're currently designing an engine for a European manufacturer at this point in time as well. And something I thought was really cool is we get these odd little, really interesting projects. And that sculpture there by an artist in Melbourne, in St Kilda area, named Michael Garrett, he approached us to create this sculpture in casting. So with that, I'll segue over to Shane. He can talk a little bit about how we could create such a cool piece of art.
Yeah, g'day everyone. Thank you, Matt. Thank you, Amber. Yes, as Matthew mentioned, the flying kangaroo sculpture of Mr. Garrett's is it's quite a complex casting. It's a really good example of how 3D printing can be utilized to create a low volume component with a high level of complexity. If you can see through the hollows underneath, there's quite a bit of detail in this. So with the design freedom allowed by the 3D printing process, we could make the printed molds for this in just 3 components. Now, I don't even know where I'd start with something like this, making it in a traditional pattern method. Yeah, so this sculpture, it was initially modeled in clay, and then 3D scanned, converted to a solid, and we took that solid body and extracted a set of molds from it, and basically we made a three-part mold, which is assembled and cast in both aluminium and bronze. So we've had quite a bit of experience with the 3D printing of sand now, and that's just one example. And we've learned a lot along the way with things like the orientation of the component in the 3D printer job box, the shrinkage allowance is just slightly different. The sand is a little bit firmer. The ventilation, there's a little bit more binder, so you need a little bit more ventilation. I feel from the sand molds. There's a lot of benefits though. You've got so much design freedom. You can design something with undercuts. You don't need draft. You can simplify molds. You can make very complex shapes with only a few components. The little kangaroo, flying kangaroo, for example, is a perfect example of that. Only 3 parts to that mold. Yeah, so we encourage all of our customers to 3D print the first of any prototype component before making any hard tooling. There's a lot of reasons for that. The first is design validation. When you've just got a CAD model and you extract a set of molds from that, it's much easier to make changes. If you've got if you need to add extra bosses here and there, it's much easier to do in a CAD model than it is to go back to the pattern maker and say, oh, sorry guys, I forgot this. Could you add this boss here? It must be a pattern maker's nightmare. They do a great job. A lot of respect to the traditional pattern makers out there, but it's very hard to make changes. Also, if you rapid prototype your first component, you have a hard product in hand very quickly. You've got an actual casting. You can then tool up and get your jigs and fixtures ready. You can work out your CNC tool paths. You can manufacture that. You can present that then to the market. It gets the product out in front of customers sooner. You can get a good market response. You gauge the market, see whether it's something you think you're going to go into production with on a larger scale. And if you are going to go into production at a larger scale, once you've done that, the tool pathing and validation and made your jigs and fixtures, as soon as you get your first batch from your foundry on hard tooling, you can hit the ground running. You can get that product to the market very quickly. So we've also integrated 3D printing and traditional pattern making. A good example of one area we've done that ourselves is in our V12LS cylinder heads. We've found the water jackets are quite complex, and there's quite a bit to them. It's very hard to make a traditional core box to make that. So we went to 3D printing the core and assembling that into a traditional pattern box. We have a video, sorry, that we've taken out at Beckworth. I think we'll have that ready to go. So we'll have a look at how we've used the traditional moulding with the 3D printed core. One of our V12LS cylinder moulds. These are a low volume production item, so we cast approximately 20 at a time. So we've utilised 3D sand printing for the complex water jacket cores and traditional moulding techniques for the rest of the pattern. Gary, you want to tell us about it?
out of the urethane resin. The core is a furane printed sand core, which is supplied by CSIRO.
So the printed core, it's a little more expensive than making a traditional mold, but it allows design flexibility. If you need anything changed before the next run, it's just a matter of reprogramming and running changing the CAD model and running the print again. A traditional core box for a core like that would probably be in the $20,000 range.
Somewhere around $20,000 for a CNC cut tool. Below that, I don't know what you pay for a wood jacket singly, but
you're looking in the $200-ish range, ballpark figure.
you get a lot of calls for $20,000 to get the product right in the beginning, and you can change it very quickly.
If the foundry's not happy, you can change it very quickly.
The other thing is you've got several family models you might make this with different core shapes.
We're actually utilising that very soon on a manifold where we're using the same cope and drag and 3 different port sets, so 3 different printed cores will use initially.
You can print option selected variations.
Yeah.
And changes for development. The accuracy on these water jackets is phenomenal. So the repetition is perfect. The fitment, because there's a CAD below, and that's CAD design as well, the clearances, everything, as you just seen, fits. It's actually pretty amazing.
With the finished casting, we've found you're down to the millimetre or less accuracy in the finished product, which makes the CNC machining a lot easier, a lot more accurate.
That's a 40 pound over the whole length.
For shrinkage, they're just in geometry. You don't get core flow via port cores. Your water jacket sits in the correct spot every time, in the same spot every time, which is something that can't be said for traditional patterns where you need to allow more machining tolerance, a lot more material to take out to get your casting exactly where you want it.
Got a fairly good shelf life. This will last a good couple of months in the urethane resin, and I believe that those cores were printed at least a month ago.
About a month.
About a month ago, so it's still really good scratch hardness. Discoloration is just when the UV light starts to go a bit brown. When they come out here, they're obviously bright greens. The only consideration that you've got with the furane sand is it's a higher resin content. In our experience, we've found that it hasn't really been an issue because the venting of the cores being printed is extremely permeable. It's not hand rammed, so it's not compacted really hard. They breathe really, really well. We've got vent holes through the bottom of the core when it's cast, and it just flows really, really nice. It's also, this is a really cold, harsh surface, smooth. It doesn't really run over that. Being printed, the metal likes to run over the core. The finish obviously isn't as good as smooth as what the core cores are, but on a water jacket, it's been fine.
And we haven't had any problems at all.
Right, very good. Thank you. Thank you to Gary and the team at Beckworth for that, allowing us to take that short video. That was a video of this actual cylinder head here being manufactured, the molds being assembled. Here's a machined one we prepared earlier. You can see the detail in that. It's a CNC ported chambers. They're as cast intake and exhaust ports. I'll roll him over a little bit. Yeah. So yeah, that's our cylinder head. That's a great example of the hybrid sand, printed sand, mixed with the traditional molds that were also CNC machined but not printed. We've got the engine block that goes with that cylinder head. This is our V12LS engine block. We developed this, our initial engine, we cut and welded two V8s together, and that basically that allowed us to prove that a V12LS at 90 degrees bank angle was going to work and be effective and do everything that we wanted it to do. Once we'd proved the concept, we decided to get into traditional casting. So I've CAD designed and modelled up this entire engine block, and then we milled out traditional patterns. To get this into production a little quicker, we 3D printed the water jacket cores because that was quite a complex part to make, and we didn't know if it was going to work and whether we'd need to make adjustments. So before we made hard tooling for the water jacket cores, we printed the first two sets. And it's lucky we did, actually, because we broke the first one in casting, and it proved that we needed to change the design, and we did. So there's a lot of other improvements on this V12LS engine block on top of a traditional LS, other than the extra 4 cylinders. We've got Siamese bores. This one's straight from the CNC, so we haven't pushed the sleeves in yet. We've got Siamese bores. We've got extra pinch bolts on the cylinder heads. We've got threaded in lifter bushes. We've got extra cross bracing, extra webbing through the engine block. We've got slightly stronger bottom end with less ventilation holes through the middle. We've got some extra, our sump is bolted on either side of the main cap at every main cap, so that becomes an integral part of the structure as well. So when we designed our engine block, we did a lot more than just make it 4 cylinders longer. So we've got one more example I'd like to show you of of integrating traditional foundry molding techniques and 3D printed cores is our Mazda rotary. As mentioned, we're into Mazda rotaries. This is a Mazda rotary intake manifold. We've made the Mazda rotary 20B center plate as a replacement item. It's a bit stronger than the factory Mazda one. There's a lot of design improvements, but it's a very complex core set. So a lot of foundries, when they saw the patterns, for the cores, they put it in the too hard basket. And we'll flip to a video where we've got Chris Beckworth at assembling a mold with the 3D printed cores, and you'll get an idea of how complex they really are. Right. So what we've got here, this is a Mazda rotary center plate. These are quite a complex part. They've got some very complex internal water jacket cores. And I've tried a few different foundries and they kept on falling into the too hard basket. And had very complex traditional patterns for the water jacket cores. And to be honest, I'm not surprised no one wanted to do them. So we tried 3D printing the cores, and that's worked really well. They've gone from a really tricky part to make to knocking out a fairly basic cope and drag, and all the complexity as in the water jackets. And I've even made 3 different iterations since printing the cores, just through a little bit of CAD design to make things give a bit more clearance where we had problems with material flow. A little bit of extra shrinkage allowance. Yeah, lots of minor changes. So this Mazda rotary centre plate is cast in cast iron. We've used the traditional, the 3D printed sand is the purine, as also used in the aluminium cylinder heads. And Chris, what are you using for the cope and drag?
That's alkaline phenolic resin.
Yeah, so that's different to what you use in the aluminium.
Yes, it
Yes.
is.
Thank you, Chris, for that video. That's a great example of how we can use the printed sand in cast iron as well and make a product that was otherwise too hard and expensive and had a lot of failures to a product that's now out there on the market. One last little one I'd like to show you is, this is a fairly simple component, but this will just give you an idea of how a 3D printed sand can be used to make small components. They're very cost effective because your print is, you basically pay for the volume. So something small like that, if you're not doing thousands of them, it's very cost effective. Right, we've probably got some questions.
Okay, Shane,
Yes.
it's Gary here. Everybody on the webcast, I haven't seen any questions come up. If you have a question, you should see
Yes.
something on the right-hand side, a question mark. If you click that, you could enter a question. I haven't seen any as yet. So, Shane,
Yeah.
so when you first started, were you printing the water jacket core for the cylinder block?
Yes, yeah, the cylinder block was, I'd made all the other patterns for it in the traditional method, and that was actually the first thing we approached the CSIRO about to use the 3D printer for. And we did that to basically save a lot of time, get the product to market a lot sooner, rather than having to do a few iterations of the water jacket core traditional tooling. Yeah, so that worked really well for us, and since then we've adopted 3D printing into a whole range of things. The water jacket for the cylinder head is the perfect example. It's great value for money, very cost effective for the smaller complex parts, particularly water jacket cores, anything like that. Yeah, it works fantastic.
Thank you. Got a question here, 2 questions actually from Alan Cook. First, how much, if any, dressing of joint lines and core prints is required?
That's a very good question. Because you're not using a standard pattern mold where you join a pattern together, your water jackets can have no seam line around them. There's no joint line. You do, however, need joint lines. For example, with this component here, you notice that core. This core has got no joint lines. If this was made traditionally, you would have a part line down here. That has no joint lines, but to clean the sand out of the mold, you do need a part line there. So when you look at this, this is unfettled. It's only very lightly fettled. You've got your seam down there, but you probably can't see there, but there's no part line on the core side. So yes, excellent question.
Thank you. The second question from Alan Cook was, please comment on the core knockout. Does the residual core drain from the casting well?
That's a very good question, and Gary Yates will tell you how good it is at you give it a knock and it all falls out. You don't need to get in there with the air chisel. There's none of that. It disintegrates pretty well.
Another question just come in. What would be the most complicated part you've made with 3D printings and what sort of cost? That was from ACAMS.
Very good question. The most complex part we've made is probably an engine that we're developing at the moment, which is another V12, a double overhead cam engine built from scratch, not using any existing components. I don't know what the cost of that would be.
The large projects like that to get into the multiple six figures. But another good one would be the kangaroo. I think, Shane, at a cost for that, that artist has spent in the thousands, not tens of thousands, to achieve a whole little flock of those guys. Shane, you want to talk a little bit about that?
Yeah, thanks, Matt. That's an excellent point. Yeah, something like the flying kangaroo. This was with no tooling cost, only a couple of hundred each. Cast and everything. It's quite complex, but it's certainly not the most complex thing we've done. But it is probably one of the more interesting and more organic shapes we've done. We're used to traditional mechanical parts where your most organic shapes are the flow of your intake ports, and then someone comes up with something like this. It's it's really interesting. We love getting different projects like that.
Thank you, Shane.
Thank you.
Gary Yates actually made a comment. He said, knockout is awesome. It's not a question.
All right, thanks, Gary.
We got another question here from Mark Gent. It was mentioned that the printed sand was more permeable than a hand-rammed core. Does this make them less stable or prone to distortion?
We haven't noticed any distortion. Our water jackets are for the V12 LS head, which you saw in the video from Beckwith. We've had them sit around for a while at times and not distort. They all fit in perfectly. The reason for the better ventilation is you've got a single sand grain size, so you don't have the fines that fill up all the small gaps. There is a little bit more resin. I may be corrected here. It's about 2% resin as opposed to 0.6. So there's a little bit more resin there to contend with, but yeah, the sand being loosely packed, not being hand rammed and not having the fines to fill in all the gaps allows the sand to breathe really well.
Thank you, Shane. I think we might have exhausted all the questions. You out there, if you've got one, you better hit the send button real quick, because once the questions are finished, we'll wrap this up. I haven't seen any more come in, so maybe this is the right time to switch over to Amber to say thank you and farewell.
Okay, well, I'd like to thank everyone then. Thank you, Gary, here, and everyone at the CSIRO. Thank you to Gary Yates and the team at Beckwith, and Amber and the AFI for allowing us to put this presentation together.
Thank you, Matt, and also thank you very much, Shane, for sharing your story with us. Thank you also to the team at Beckwith, ferrous and non-ferrous, for allowing some filming to take place. And last but definitely not least, thank you also to Gary for putting this together allowing the filming also to occur in Lab 22, and I suspect giving Steven Spielberg a little bit of a run for his money. Thank you for joining us, everyone, this evening. We hope you've enjoyed tonight's presentation as much as I certainly have. Absolutely fascinating, and I'm not really a petrol head, so it's quite amazing what you guys are doing over there, and I'm not surprised in any way, shape or form about why everyone is so enthralled and fascinated with what you do, how you go about doing it, and the growth you experience. Just finally, I want to tell all our members how much we have enjoyed seeing you via this webcast. We do hope next time we meet, it'll be live at our AFI Legends presentation night. It was originally planned to be held on Wednesday, the 8th of July. Depending on what happens next week, and then I guess perhaps within a couple of weeks after, we may or may not be able to hold that then. But please stay tuned, and we will be sure to keep you updated via emails, via Facebook, to let you know when that's going to happen. In the meantime, thank you all for joining us, and we look forward to seeing you again.